All right. Okay, so let's get started. I think we have most of the people. So today we're going to cover sequential logic. This is actually a very important lecture. Okay, when I say important, I really mean it. Okay, so today we are going to introduce quite a few new concepts, a latch, flip-flop, and clocks. So some of this concept may appear, somewhat convoluted at first. Okay, so that's where I'll try to slow down and really try to give you the intuition. So once you guys get the intuition, hopefully, the ways these things are constructed will appear quite natural, fairly natural to you guys. All right, so but again, so this is a very important lecture. So in case you have questions, please do stop me and ask. Oh, so somehow I forgot to post the lecture slides today. Sorry, Katie. This is already too late. Okay, but I'll try to do that next time. Thanks for reminding me. Okay, so just a few logistical issues. We're going to be posting lab 2 today. This lab will contain another tutorial called Verilog tutorial. Make sure you guys try to finish this tutorial as early as possible. This is going to be useful, very useful for your lab 2. Okay, and also, if you haven't received the FPGA board yet, or you're not able to install Cortex on your computer, so make sure you email us right away. Again, you're going to be using these things for lab 2. I know some of the computers that you have may not compatible with Cortex, so we're actually working with IT to come up with a workaround. So most likely, we will need to provide cloud access to a Linux server. But the problem is that even with this cloud access, you will later on still need to use a local Cortex, the proven FPGA. But at least for now, that should allow you to at least do some simulation and test. Okay. And also homework 1 is due tomorrow. If you have questions, come to office hours. My office hours in this afternoon. All right. So first, let's just quickly review some of the things that we covered last time, right, on Tuesday. This is the quiz that you guys did on Tuesday. Then we learned about mux, right? It's a 4-to-1 mux. We learned that we can use a mux to select, right, so multiple inputs. So and then we connect one of the inputs to the output, right? And by using this property, we can also use mux to implement Boolean functions, right? Of course, combinational logic. This is a quiz, right? I think most of you did very well, right? So really the interesting part is these two inputs, right? So if you look at this input, right? So this is input 1, right? We're looking at these 2 rows, right? So this is where A, B are 0, 1, right? And we basically check, right? So the C input and the Y output, in this case, they agree, right? So they are consistent. So that's why we just set Y to be C, right? And also, if you look at this one, right? So this is where AB is really 1, 1, right? And again, check C and the output. So this is where Y is opposite to C, right? So that's why we put C not there. Okay, so this is a quiz. Last time we also talked about this 4-to-2 encoder, right? So encoder is opposite to decoder, right? So with encoder we have more inputs, right, than outputs. So for the specific kind of encoder, so let's say we have 4 inputs, right? So only one of the input will be hot or 1 at any given time. So this is a given. This is how we define a specific encoder. So it's actually over here, we have 4 inputs, right? I3, I2, I1, I0. So essentially, they basically encode the index of the output line, right? That will be asserted, right? So this is basically what these inputs are doing. I asked one question, right? So last lecture. So I did ask, right? So if you look at, for example, Y1, somehow Y1 only depends on I2 and I3, right? I0, I1, so they are not even in the picture, right? So what's going on? I think we did agree that, right? So if you look at this truth table, this is, right? So these are not really, right? So we only have 4 rows here. So this is not really a complete truth table, right? that's where, okay, so we can make use of don't cares, right? Okay, right, so again, some of you are asking, right, so again, I actually forgot to post slides, right, so this is my bad. Before the class, I'll try to avoid this mistake. Okay, unfortunately, it's too late for me to do that. It's usually take quite a few minutes for me to do that. So I'm gonna post it right after class, right? Okay, but coming back to this encoder, so let's just try to figure out, right, so what's going on, right? So we can actually draw a kernel map, right? There's a 4 input. We can still handle this with the K map, right? So we put in 1 and zeros. So we already agreed, right? The rest of this right, cells are just don't cares, right? Okay, so let's look at, again, this is the K map for Y1. If we do there's a prime input, we do the circle, what is this? What do we have? Very good, right? This is I1 not, I0 not, right? But if you look at this circuit diagram, what we have is I2 plus I3. Is that right? Why the discrepancy? What's going on? Am I drawing the wrong circuit diagram? Can I circle a larger one? Is there a larger one? Okay, very good. So one of you saying, Katie saying, right? So why don't we do this, right? So this is, we are doing SOP, right? So if we do POS, we can focus on zeros, right? Oops. So what is this? This is I2 plus I3, right? Right. But we also agree that, right? So actually POS and this right, SOP, so they're supposed to be equivalent, right? So they are just different forms. Why are these two equivalent? Just think about the definition of the encoder, right? So by definition, exactly only one of the input is a 1, right? So you look at this term, right? This expression, it basically says that I1 and I0, they are not ones, right? What does that imply when you further consider the definition of this encoder? It means one of the other outputs, right? In this case, I2 and I3, one of them must be 1. Make sense? Right? So they are indeed equivalent for this specific problem, right? For this specific circuit. Okay. Again, we can actually draw circuits, right? So there are actually different ways. This also tells you. So it's not like, this is the only legal diagram, right? For the circuit diagram for the encoder. All right. Okay. So I think there are more questions about whether we can circle more things or not, right? So try to convince yourself, right? You cannot circle the top row and the bottom row because there's a 0 there, right? And you also cannot circle the first row and second row because there's a 0 there, right? All right. So let's talk about the sequential logic. Right. So we are already familiar with convolutional logic, right? So this is where we have, right? So usually we draw inputs on the left-hand side and outputs on the right-hand side. Okay, so looks like some of you have more questions about this one, right? Let me just try to, although this is, this should be clear to you. So once you actually look at this in more detail, right? So just tell me, like, how do you draw a bigger circle? Right? Since you guys are not convinced, right? So there's no bigger circle. Second and third column? Yes. Right. Very good. Sure. So that's another way to do this, right? But what about the 0 in the last row? You still need to cover it, right? Ambrose? We only need one circle to cover everything in this case, right? Oh, you're thinking of SOP or PO. Anyway, so if you guys have other proposals, let me know offline, right? So, but the point here is that this is not a kernel map lesson, right? So I just want to make sure that you guys understand, right? So why? So we have this SOP form is different from the POS form. Why this makes sense, right? For this specific problem. All right. Okay, coming back to the conditional circuit, right? Again, so this is something that we're already familiar with, right? The outputs for conventional logic depends only on the current inputs, right? Okay, so this is a simple definition. And in contrast, I briefly mentioned the definition of sequential logic. So this is where the outputs not just depends on the inputs, it also depends on the past history, right? So it actually remembers some history. So that's where we have this feedback path. Okay, so this is how the feedback path come from, right? And this is the focus of this lecture, right? How exactly do we store this kind of history? So we actually use this so-called state or storage element. So basically, we want to be able to include some memory in our circuit, right? Which remembers the past. And one important thing is, so for sequential logic, right? So we usually, when we even draw the circuit, we usually have this kind of feedback path, okay, like this. That's where we have sequential logic. Then you have basically like loop, okay. And for conventional logic, right? So basically the circuit diagram is like feeding forward. Right? Okay, but this is fairly abstract, right? So let's try to be more concrete. So again, I'm just repeating the same thing that I just said, right? So for a sequential circuit, output depends on inputs and some state variables. So this state basically represent or capture some of the past history of the circuit. By past history, usually, this is the output that's produced by part of the circuit in the past. And we are going to be introducing these so-called storage elements. Okay, so we are going to talk about how do we construct such elements, such memory to hold this history or hold the states. And of course, I've been talking about past and present, right? So what exactly do I mean? I have to introduce a notion of time, right? So without a notion of time, right? So there's this is sort of meaningless, right? To define past and present. So that's where we need to introduce the concept of clock, okay? So this is another important concept that we are going to talk about in this lecture. All right, so let's talk about storage elements first. Okay, so let's think about how exactly do we store information using the logic that we have learned so far. We already agreed that, right? So combinational, this is a conventional logic. Let's just use inverter, right? The simplest kind of gate. So this is combinational, right? So this cannot store any information. When we change input, output is going to change right away, right? Okay, but what about, we talk about feedback, right? So with sequential logic, we usually have some feedback, right? So what if we do this? We connect the output of the inverter to its input. Can we make it remember things? Can we make it hold a specific value, whether it's 0 or 1? Does it work or not? Any opinions? Okay, so I'm creating this self loop, right? Basically. So let's say initially this inverter output 0. What are we gonna see? What are we gonna see next? Right? It's gonna alternate, right? It's gonna go to 1, right? Very good, right? After that, it's gonna go back to 0, right? So this is gonna keep oscillating, right? Or keep inverting. Make sense, right? So this does not quite remember things, right? It's like oscillating all the time. if you only do a single inverter and then create a self loop. Right? Again, I'm connecting the output of the inverter directly back to the input. Right? So what's the fix? Yes, very good. So we put, how about 2 inverters, right? Still, we create this loop, right? So now that we can store something, right? Now, if this is 0 initially over here, right, for the first inverter, and over here, we're going to see a 1, right? So let's say we drag this out. So we create an output pin, let's say Q. Okay, we're going to be using Q a lot, right? And Q is going to be stable at 1. Does it make sense? Right? Because we have a 1 here, it's going to be 0 and 1, right? Okay, let's, hopefully you guys are convinced, right? So this is somewhat stable, right? But the question, right? So, Alma's already asking a very good question, right? So how exactly do we write to this thing, right? So, we don't really know what we are storing. So this is sort of depending on the initial condition, right? So you put in 0, then it's going to be 0. So we'll be stuck with a 0 value, right? Or 1, right? So in this case, we're stuck with a 1 all the time. But unless you guys are convinced, we are storing something, right? And as long as these inverters are powered, we are able to hold this value. Okay, so this is actually so-called the bistable element. It's actually the most basic kind of a storage element. So basically, cross-couple, right, 2 inverters. Look at this diagram, right? So this is sort of like twisted diagram, right? The reason we are doing this twist is I just want to make sure that the outputs. So over here we are dragging out 2 outputs, right? One's Q, the other one's Q naught or QN. So they are laid out on the right hand side, right? Just following our convention. That's it. So really pay attention to this one. So although these 2 wires seem to be crossing, they are not connected. Okay, so that's why we have this curve right over here. All right, so we already talked about this, right? So this is basically a sort of a storage element that can hold something, right? But why is it called bistable? It's called a bistable element. That's because, right, depending on the initial condition, right? We can, so initially we have a 1 here, right over here. So Q1 will be 1 all the time. Qn will be 0 all the time, right? Or it could be initially, so we have 0 here, right? So this guy will be 0 and this guy will be 1 all the time. So basically we have 2 stable states, right? So this thing can hold either 0 or 1. But the problem is that we cannot really write to it, right? We cannot really change the stored value. All right, so hopefully this makes sense so far, right? Okay. So what's the fix, right? So how can we write to this element? So right here we have inverters, right? So with these inverters, we have a single input and single output. So look at this inverter. So both input and output pins, they're already used, right? Looks like there's no way that we can further add things to this, right? Further connect wires to this elements because we want to write it, right? So we want to provide additional input. So how do we do that? So maybe we can replace this inverter with a 2 input gate, right? So that's the one proposal, right? How about, let's see whether it works or not. So maybe we can replace it with something that we learned right before. What is this? This is a NOR, right? This is 2 input, right? Okay, and we can also replace it with both inverters, right, with NOR. Okay, let's try this. Later we'll see NAND as well. We can also replace the inverter with NAND. But for now, let's just focus on NOR. Okay. But we still wanted to hold things, right? We still wanted to remember the state. So what do? We have to make sure that this NOR can implement the inverting function, right? The inverter function. So this is something that we already learned, right? So let's see. Okay. First, hopefully the high-level idea makes sense, right? So we want to open it up somehow, right? So we want to introduce one more input, okay? So we can write it, for example, this input. So we can, connect it to something outside. So we can write it to it. So you can provide additional input. So that's why we, replace this one input inverter with a two input NOR or NAND. But let me help you guys refresh your mind a bit, right? So we talk about the behavior of NAND and NOR, right? So how do we implement inverter with a NAND and NOR? So on the left-hand side, we have NOR, right? It's what? So this is basically identity element, right? Okay, for OR gate. So if you put 0 here, we have an inverter, right? Make sense? X or 0 is X, and then we invert it, we have a bubble, okay? And for NAND, it's the opposite, right? 1. So that's how we get inverter, right? Using NOR gate or NAND gate. All right, so this seems hopeful, right? This seems promising, right? Unless, we can still implement inverters using this, this two input gates. And looks like we can actually provide additional input, right? So since now we have one actual input pin. All right, so before I talk about this new concept called Latch, let's review another concept, which is something that we also discussed last time, right? When we talk about XOR, right? Ask you guys about the so-called NAR element. So this is also extremely important. Okay, so for understanding the concept of Latch. So we talk about this so-called NAR element, right? So basically, this is something that if you do X and we do X, let's do this. Right? This is basically NOR, right? We want to do X NOR this thing, so we want to get the 0, right? Regardless of the value of X. What is that value? What value do we put in? Very good. Okay, 1. So remember this. So this is very important. Okay, again, I want to say very important. So 1 is NAR element for NOR, right? So here, the high-level idea here is that, so we don't care about X, okay? If you put in a 1 here, the output is going to be 0, right? Regardless. So as long as one of the input is 1, so the output is going to be 0. How about NAND? Opposite, right? 0. Okay. All right, clear so far, right? Hopefully, this is not too bad, right? But we can use NOR or NAND to implement inverter, and we have this something called the NAR element, right? So basically, clear out things, right? So we don't care about the other input. Once for NOR it's a 1, then we have 0. For NAND, if it's 0, we have 1. Okay, so this is the same NAR element, right? For NOR, it's basically the same as OR, right? 1 is also the NAR element for OR, and for NAND, it's the same as AND. Okay, so if you guys understand this thing so far, the rest will be much easier. Okay, so now let's look at the first useful, this so-called basic storage element. It's called a latch. Okay? It's called SR latch. The full name is set reset latch. So it's named after the two inputs. Okay, one is called R, the other one is called S. R means reset, the other one S means set. All right, so I'm drawing this thing again in a slightly different way. So I'm actually changing different forms just to make sure that you guys are not really sort of fooled by or confused by the different ways we draw things. Okay, but really this thing is also a sequential element, right? Sequential logic, because we do have a feedback here, right? We are basically connecting two NOR gates, right? These are two NOR gates. All right, so how does this work? So let's try to reason about this. Okay. First, let's look at this truth table. Okay. So you don't try to write down the Boolean instruction. Okay. For understanding things, you really don't need to write down any Boolean instructions. So that's something that I really want to convince you. So let's just try to get intuition. So when S and R, they are both zeros, what does the NOR gate do? When S or R are both 0, what exactly is the NOR gate? What is the function of the NOR gate? Inverter, right? So both inverters are regressing to the form of, sorry, both NOR gates, right, are regressing to the form of inversion, right, inverter. Make sense? When both of them are zeros, they are just basically two inverters. So then what is Q, right? So over here by Q next, so this is the, right, the notation I'm using in this lecture, right? Q next really means that since we have the notion of time here, right? So I'm going to introduce that. So really when this R or S changes, the input changes. So basically, what's the new value of this Q, right? The Q output. So in this slide, we don't care about. Let's don't care too much about Qn, right? Let's just focus on Q. All right. So Q is going to be what? It's going to be the last Q next is going to be last Q, right? Because we are doing two inverters, and these are both zeros. Make sense? Right? They are just holding. They are basically just inputting this basic bistable element, like what we just saw. All right. So second row, when R is 1, over here, when R is 1, what do we have? What is Q? Q next. Very good. 0, right? Because 1 is a NAR element for NOR gate. Again, think about NAR element. So the moment we have 1 over here, right? The moment we have 1 over here, Q is going to be 0, regardless of what's going on, right? In the rest of this, seemingly convoluted, right, self loop, right? We don't care. We don't care about Qn, right? Okay, so we just talk about, right? So the first row is called hold, right? We're going to use this term hold. It's basically holding the state, right? When both of them 0. Second one's when R is reset signal is 1, we are resetting. Okay, we reset this latch. So we're going to write 0 into this latch. Okay. Next one, 1 0. When S is 1. Okay, when S is 1. Okay, S is 1, right? So what's Qn? Right? So really over here we ask Qn, right? So 1 again is a NAR element, right? Qn, regardless of what's going on in the past, right? Qn is gonna be what? A 0. Right? Qn is gonna be 0. And R is also 0. Right? So then Q, of course, is a 1. Right? Since this is the NOR gate. So this is called set. Okay. So for set, focus on S, right? So this is where we have a 1. Any questions so far? Does this make sense? Right? It's all about understanding the intuition, right? So when both of these first row, so that's where we are holding, right? Both of them are inverter. Okay, second row, when R is 1, okay, so we have a NAR element, right? So effect. So we really don't care about what's going on in the past, right? Same thing for set. Okay, so both reset and set. Okay, that's how we write 0 and 1. That's how we update the state. All right. So we're gonna be worrying about this thing later. Okay. Actually, the last combination is something that we don't want. This is actually a risky or dangerous combination. I'm gonna explain this. All right. Again, if you have questions, ask me. Okay. So there will be a quiz in a couple of slides. Right. I'll show you a different latch. Right. If the intuition is not clear, right, make sure you either just unmute or type something in the chat window. All right, so okay, so this is the the truth table that we just saw, right? But with two expanded columns, right? So I'm not gonna really elaborate too much on this line, right? This is actually the brute force way. Okay, this is the way that I don't want you guys to care too much about. Okay, but if you really want to reason about things, right, you can actually write down the Boolean expression as well, okay, for the circuit. And this is the form, right? You can actually write Q next, right? In terms of R, S, and the previous Q. And this is the actual Boolean expression. And you can just plug it in. You can create an expanded truth table. and that's how you can get the final output column, right? But don't worry too much about this, right? So later on, we're going to do homework, we're going to do exam questions. So for this kind of latch, you really don't have to write Boolean instruction like this, right? So this is not the right way to reason about things. The right way to reason about things is really about when does this latch hold state? When does it set? When does it reset? Okay, all right, so there are some questions, right? I was asking, how does anything pass through the gates if the second gate cannot produce an output until the first gate produce an output, but the first one can produce an output without the second outputs? Or is it giving another elements? Right, so interesting question, right, Alma? I'm not sure I fully understand. Maybe you wanna unmute? Do you want to clarify? So what do you mean by this question?
Yeah, I'm just confused how, like, if you look at reset and it's connected to the NOR, but the NOR needs to get QN before it can give a value, but then QN isn't produced until the NOR before it.
Right.
Yeah, that's my question.
Okay. Yeah, very good question. Right. So that's why very good question. That's why I'm trying to discourage you guys from looking at this kind of Boolean instruction. Right. So instead, all I want you guys to understand is when we do reset, right? So we put a 1 here, right? We really don't care about, right? So QN, right? We don't really care about the value of QN, right? So when is it produced? How is it produced? What's the value? It doesn't matter. Does it make sense? Right? Because we have 1 here, and based on the property of this NOR gate, so we are going to be seeing a 0, right? Okay. And of course, so usually you might be thinking about timing as well. That's something that we're going to be talking about, right? So this means we usually hold R and S, right, stable enough, right? So that's not going to like glitch or oscillate, right? So let's just think that we hold R and S stable enough, right, for a period of time. So when R is 1, Q is going to be 0 for sure, right? Okay, so right, so yeah, Steve is right. So basically, this is really about NAR element, right? So the rest is irrelevant, right? Okay. So what if the very first input is 0, 0? Shiba's asking, Shiba, what's your question? So what if so this is 0, 0, right? So you're saying this R is 0, S is 0, right? So that's where, again, don't worry about the Boolean instruction. Don't try to come up with a Boolean formula, right? So when both of them are zeros, we just talk about this, right? So these two things will regress, right, to 2 inverters. Then both of them are zeros. These 2 NOR gates are basically 2 inverters. And that's where we are holding, right? That's where we are holding the state. Okay, right? So again, what are exactly do we hold? So that depends on the previous state. All right. Okay, so let's do some exercise, right? Just to help you guys. Again, so we want to understand, right, what is hold, right? Again, this thing, you may need to wrap your brain around a bit, right? So, but really try not to reason about, what happens first and next, right? So this really doesn't matter much, right? So you're about NAR element, and when do we have 2 inverters? Okay, so we just talk about, right, when RR is 0, right? So we hold this is right related to what Shiba was asking. Let's exercise a bit, right? So this is not a quiz, right? Same thing as our latch. We initialize this latch with a 0, right? So I'm going to input a sequence of R and S, okay, to this latch. So first I'm going to set S to be 1, R to be 0. What is Q after that? S means set, right? Set means we change Q to be 1, right? All right, very good, right? So we set Q to be 1, right? And all right, so after that, I change S to be 0. R remains 0. What is Q? Okay, so Q is Q last, right? What is Q last? Q last is 1, right? We just change it to 1, right? Okay, next, I change R to be 1. S is 0 now. Okay, this one. S is 0 now. R is 1. What is Q? Okay, very good. 0. All right. Looks like you guys are getting the hang of it. Okay. So we reset, right? So when R is 1, we reset. Any questions? Any more questions? Again, the quiz will come up pretty soon. All right. If not, let's see. Okay, so let's look at this interesting combination, right? And mostly I'll not test you guys about this right later on, but still this is useful to discuss what's going on, right? Then we have a combination like this, and S and R, they are both 0. Okay, when S and R, they're both 0. So this one, oh, sorry, when S and R are both 1s, okay, I was referring to this too. When S and R are both 1s, okay, so we have another element, right? This is another element effect. So Q will be 0, right? And Qn is also 0. Make sense? Right? Right? Yeah. Right. And now we are going to talk about why we want to avoid this. Okay. So very soon. And Ashley is asking, so when S is 0, R is 0, yes, right? So that's where, again, when R is 0, S is 0, we basically have two cross-coupled inverters. So that's a stable, right? So that's a stable storage element. So that's where we are holding the state, right? It's basically a self loop, right? Self-reinforcing loop with two inverters. Okay, all right. So coming back to this combination, right? SR on both ones. So we're already seeing this annoying thing, right? So somehow Q and Qn, they're not opposite to each other. Okay, that's already annoying, right? So what if I want to use Qn, right? So but now this is not Qn not. Q is not Qn not anymore. But is it a real problem? So someone may propose, who cares about just the internal state, right? Internal signal looks like an internal signal, right? Qn. So why don't we just add an inverter like this, right? And then call this Qn. How about we just fix it like this, right? Then this Qn would be 1, right? This is a new Qn. That's a Qn star. Okay. So this might be a interesting idea, but turns out that our problem runs deeper than this. Okay, we are actually in a deeper trouble. Once S and R, they're both 1s. So let's see what's going on. Okay, so again, first S and R both 1s, right? So we have Q, Qn, they're both 0, right? So now let's say I change my sequence, input sequence. Okay, it happens that the user of that wants to hold now. It wants to hold the state. Change the sequence to SR to be 0, 0. Okay, so become 0 and 0, right? So what is the new Q and Qn? What is that, right? Right, just to be clear, right? So so the previous state, in the previous state, okay, Qn 0, and Q is also 0. That's the previous state, right? Now my new input is S is 0, R is 0. Suppose I want to hold, right? Okay, I want to hold the same state. But this is where you can quickly find out, right? So since this is 0, right? R is 0, previous state Qn 0, the new Q will become 1, right? And Qn will also become 1. And we can keep holding, we can try to keep. And this is something you guys should try to figure out. What is this? Okay. So actually we will come back to 0 again. And basically this thing breaks, right? So it's no longer holding. So with our internal state, it's already messed up. right? When S and R, they're both ones. It's sort of messing up our internal state. And we can no longer hold. All right. Okay, so this is, just want to help you guys understand why we actually want to avoid this. Right, so there are some questions about, right, so can you explain why the last line is 0, right? She's asking, right, I'm just saying, this is, I'm keeping R and S to be 0, right? So my new state is Q is 1, Qn is 1, right? And if you just look at this, how this gate functions, you'll see some of this output will change back to 0, right? Because 1 is another element, right? The moment you have 1, right, on the input side for NOR gate, output will become 0, right? And this order, so right, almost right. So this is one potential, right, behavior when we see the oscillation, right? Depending on timing, we may see different kind of, but regardless, the internal state is messed up. Do you guys agree? Right? So we do want Qn and Q to be opposite to each other, right? That's how we can internally hold state. All right. Okay. Any more questions about SR latch before we do the quiz? Okay, so one more latch, okay, before we talk about another concept. Right? This one is called D-latch. So with D-latch, it's actually built on top of SR latch. So this is where we actually avoid. So with D-latch, we can avoid illegal combination, right, for SR. We don't want SR to be both ones, right? So with D-latch, we can actually avoid it in a very clever way. And also, we can decouple two concerns. We can have these separation of concerns. So with SR, one is called set, the other one is reset, right? So basically one set 0, one set 1. But with D-latch, so we decouple what kind of a value do we want to set and when do we set it. Okay, we have two signals, one's called D, the other one's called C. And later we'll use this term a lot, right? So we have open close, right? So when the latch, D-latch is open, we are allowed to, the latch allows new value. We can take new value. So basically the input flows through to the output. Otherwise closed, it's basically holding state. All right. All right, so these are the sort of the abstract concept. Right, so let's just quickly look at the what exactly is a D-latch, right, and how do we build it. So we have two inputs, right, not SR anymore. So we have something called C and D. Okay. So C is it was pretty soon. So what kind of a signal do we connect to C? But C for now just an enable signal, the right enable. If C is enable or 1, okay. If it's a 1, so Q will be the same with D. The Q output or Q next, right, will be the same with D. Otherwise, if C is disabled, if C is 0, disabled means 0, okay, then output does not change. We retain the last state. That's how we remember things. Okay, so let's look at how do we build a D-latch over here. So we have SR latch, right? So this is something that we're familiar with, right? Already, hopefully. So we have two cross-coupled NOR gates, right? And according to the definition of D-latch, so when C is 1, we can take new value, right? So that's where if D is 0, so we want Q next to be 0. Okay. So Q next here means that the new state of Q when D or C changes, right? So to make this happen, what is the R? What is the S? Just tell me. Can you guys fill in the blank for the first row? What is R and S? So we want to set Q0 to be 0, right? We want to set it to 0, not hold, right? It's a reset, right? Because we want it to be 0. Make sense, right? Next row. So again, this latch is enabled, so that's where we can change the state. And we want to change the state to 1. So that's where we have a set, right? What is that? 0, 1. Okay. Last row. C is 0. C is the enable signal. when C is 0, it means the whole latch is sort of disabled, meaning that we hold the value. Right? So how do we hold the value? 0, 0. Okay. Once again, so when we have 2, 0, 0, we have 2 zeros for R and S, we have 2 inverters. Right? Okay, so then we can just write down the Boolean instruction here, right? So what is C according to this truth table? Sorry, what is R? Right? Let's write. What is this signal? So what do we connect to this signal? Right? How do we do this? Right? So R in terms of C and D, what is that? Right? C naught. Right? S in terms of C and D. S. CD. Okay, that's it. So that's how we make a connection. Right? Make sense? So we just need to add a few more gates on top of SR latch. Then we have a new kind of latch. And this is the kind of latch that we'll be using a lot later on, because this is nicer to use, although this is slightly more expensive, right? So this is indeed more expensive in terms of number of gates. But we can easily avoid the input combination, right? See here, just see this right, R and S columns. So there will be no 1, 1, right? R and S will not become 1, 1 at any given combination for C and D. And also we can choose to control. So we can choose when to set a new value and what kind of new value to set. Right? Any question about D latch? This is right. D means really we are using the D means data, right? In this case, this is the input data. All right. Okay. So this is basically the truth table that you guys just saw, right? And this is the symbol that we use for D latch. Right? Again, input on the left hand side, output on the right hand side. So QN, I think just to re-answer the question again, right? QN is the inverted version, right, of Q. So that's why we have bubble here. This is D latch, right? If this is clear, right? So let's look at right. This is actually 1-bit D latch. We can also build a more complex, right, multi-bit D latch. So what we do here is basically we have, right, so this is a 4-bit D latch, right? On the input side, we have D1, D2, D3, D4, right? Output side, we have 4 bits, right? So that's how we can hold, right? So 4-bit information, right? If C is 0, let me ask you guys, if C is 0, so maybe let's say, I'm holding initially I'm 0, 1, 0. Okay, when C is 0, what is the next state? Same thing, right? Same thing. So when C is 0, so C is really enabled. When C is 1, Q1, Q2, Q3, Q4 will be the same. It will become D1, D2, D3, D4. Okay, Q will capture D. So when we store things, we often just call it, we latch on, right? So this value is latched on in this storage element. That's why it's called a latch. All right, and we are using, in this case, C here, we are using the same C, right, to drive each one of this latch. So what exactly is the C, right? So what kind of C do we usually use, right? That's where let's talk about